Hi, Andrea here. In the previous video we had a first walk in the world of sets. Now it's time to move forward, better explaining the operations of union and intersection of sets. Let's take two sets A and B. As shown, their union can be described as the set of all the elements belonging to A or B, while the intersection between them can be depicted as the set of all the elements in A and B. To better understand these concepts, we can visualize them using a so-called Venn diagram. It is a visual representation that shows logical relations between sets, popularized by the English mathematician John Venn in the 1880s. A Venn diagram exploits our idea of thinking sets as bubbles containing a collection of elements. We can say that if two sets have some elements in common, they overlap. In the part in common, we have elements shared by the two sets. That is the intersection. Instead, the whole agglomeration of the two sets together is the union. Now, we can consider some special cases. What if two sets do not overlap? Well, in such a scenario, there is no intersection. In other words, the intersection is the null set or empty set. Also, what if one set contains the other? In this case, the union is just the bigger set. For sake of completeness, there is even a formula that links union and intersection, also valid in the general case. This chunk of math tells us that the union is formed by all the elements in A, all the elements in B, but then we have to delete the part in common in order to not count the intersection twice. These are just simple examples, but everything can be generalized with any number of sets. Let's say we have three sets, A1, A2 and A3. The union is again constituted by all the elements of the sets. Instead, the intersection is the common part of the three sets. In this case, the union formula becomes as you can see. I know it is not very attractive and it is so large I had to change the font size, but digging into it can be helpful for a better understanding of what is going on. Here, to build the union, we need to add the first set, then the second set, and then the third one. After that, to avoid double counting, we need to subtract the intersection of the first two sets, the intersection of the second set and the third set, then the intersection of the last couple of sets. But now the central part of the diagram is not included, so we need to add the intersection of all the three sets. To sum up, it is important to add all the sets, considering each piece in the diagram the right number of times. With this in mind, the formula is not scary anymore, isn't it? Furthermore, this formula can be written in a more compact way. To indicate the union of the sets, it is possible to use the following notation, which means we are considering the union of every AI from A1 to A3. In a similar fashion, we can write the addition of the three sets as the sum of each AI from A1 to A3. In a similar way, we compact the sums of their intersection. Such a formula can be easily generalized to the case of n different sets. The idea is again putting together the sets and counting the intersection between them the right number of times, adding and subtracting the required pieces. Finally, we have a nice knowledge about sets. In the next video, we are going to connect sets to logic.